give you a quick run through. And then if you are out on LinkedIn or YouTube, I'm not going to go through those specifically, but if you have a question, drop it in the chat. We'll capture those questions, bring them back here, and at the end, we will go through a little bit of Q&A with Umesh. If you're in the webinar platform, the things that you need to know are down at the very bottom. There is a menu that allows you to navigate through some various features of the console. Most important ones are the chat one, and I'll send a message there in a second letting you know this is where you can talk. And then right next to that is the questions button, and obviously you know what that does. Go in, click the button, click new question, submit it there, and then at the end, we will go through all of those with Umesh. Everything else is probably pretty self-explanatory, so I'll let you ping me in the chat if you have any questions about those specifically. But I want to make sure we maximize our time today, so I'm going to hand it over to Umesh. Umesh, don't forget to reintroduce yourself to the community and then take it away.
Yeah. Hi, everyone. I'm Umesh. I'm an embedded system consultant from past 10 plus years. And I've been writing embedded software for IoT solutions for, I think, a decade now. And yeah, that's all my introduction is. So today we will look at how to add the Ethernet connectivity to the microcontroller, and we will be using WIZnet W5500 module and STM32 microcontroller. So before we get started with the presentation, I want to show you some magic. And you can see on my screen, I have a serial client opened here on the left side, and on the right side, there's a TCP client here. And let me show you a real physical demo. So you can see on my screen here, on my hands, there is this STM32 microcontroller. And we have this W5500 module from the WIZnet. So we will be setting up the TCP server onto this STM32 microcontroller, and this server will be accessed through this Hercules TCP client. So we are using here a TCP client here, and this is an IP address of the TCP client. So let me just disconnect and show you. Let me click on connect again. And you see now the TCP client and server connection is established. And on the left side, you can see the TCP client is connected. So the first magic that I want to show you is the auto negotiation feature of this W5500 module. So what happens is when I disconnect the LAN cable, so this is our this is our TCP server, and let me just disconnect the LAN cable and see what happens. Okay. Okay, so let me just disconnect and reset. You see, it continuously print on the left side. It says waiting for link to be established. Okay, so that means the link is not established because we have disconnected this LAN cable. I hope everybody knows in the Ethernet what the LAN cable is. And as soon as I plug back in to this LAN cable, see what happens. So I have connected, and you can see quickly it detect again the TCP server listening to port 5000. Okay, so it's automatically detect. So when the link disconnect, the physical LAN disconnect, it detects and it says it's not, the link is not established. And as soon as it connects, it's automatically detect. And we'll talk about it, the auto negotiation feature. The other thing that I want to show you is, so connection is closed. Let me click the connect button. On the right side, you see the TCP client is connected to this server, this physical hardware in my hand. And you see there are two options here. There is a message on and there is a send button. So let me click on send button, and you see the LED lights up because we are sending from this TCP client. This is our TCP client now. Look at this. This is our TCP client, and we are sending message on to the server, and server is sending back this text message LED on. Now there is a second message. I have this message off text, and when I press the send button, the off will be sent, and you see the LED goes off now. Okay, let me send off again from client to the server. LED light up, and when I send off, when I press the send button, and it goes off. So this is a typical client and server communication happening over this LAN cable and using Ethernet using W5500 module from WIZnet. And this is the demo that we will be implementing onto our physical hardware today. Okay, I hope this set the stage and the foundation for our presentation. So let me now go to presentation. And this is the first slide. As I said, we will be learning how to implement the Ethernet connectivity into the microcontroller. So we're going to start off with an overview. First, we will spend some time to talk about W5500 module, 5500 PHY chip. Then we will talk about the driver library because Visnet provide very amazing IO library. And then we will get into the network configuration. The way we will establish this TCP client and server communication is creating a small network. And we will put the static IP address. So I will show you how you can set up your own network configuration. And then I will get into the interfacing, like how you can interface W5500 module with the STM32 microcontroller. I will be using this Nucleo 32 board, the low-end STM32 microcontroller, because you might argue with me sometimes that some STM32 microcontroller has a built-in Ethernet controller. So I'm not talking about those. I'm talking about low-end microcontroller which doesn't have Ethernet connectivity, and we want to put the Ethernet connectivity from the outside. Okay. So then we will dive into the TCP client. We will be using Hercules, which is a free software. And then we will get into the live demo where we will implement a TCP server onto STM32 microcontroller using W5500 module. Then we'll summarize all the things that we have seen so far. The interesting thing that we want to discuss here is we will compare all the possible solutions, especially the popular one in the market. And then I will give you a very detailed abstract, like how would you choose the Ethernet PHY for your project and your requirement. And then for sure, towards the end of the session, we'll take a question if you have any. And if we run out of time, in case, I don't think so, but if in case we run out of time, feel free to drop your question into our amazing Discord server. So let's talk about this Visnet W5500 chip. So this chip is amazing because the integration of the TCP IP stack is very simple with this chip, and it has a built-in TCP IP stack. And it supports auto negotiation feature. That means whether your network connectivity is 10 Mbps or 100 Mbps, whatever the speed it is, it automatically detects and understands and then adjusts itself. So you don't have to configure by yourself externally. The chips takes care of itself. The way this W5500 module will talk to any microcontroller is over SPI SPI interface. So if your microcontroller, any microcontroller, even if it's a 8-bit microcontroller, if it has an SPI interface, then you can connect this Visnet chip and then give the Ethernet connectivity to your project. And we will be using mode 0 SPI mode to communicate. Full and half duplex supports. It supports 10 and 100 Mbps speed, so it's really high speed. This chip has a 32 kilobytes of memory, and this is really amazing because the chip itself has a memory. Even if your microcontroller has a less memory, still this chip can offload all the TCP IP heavy lifting stuff into the chip itself, W5500. That's amazing. And into this 32 kilobytes of memory that this chip has, 16 kilobytes is reserved for the receive buffer and 16 kilobytes is for the transmit buffer. We'll get into that all the more details about it. This is very, very important because the chip itself has the feature and the memory. Then this chip supports hardwired TCP IP protocol. It thus supports all these great features like TCP, UDP, IPv4, ARP, and a lot of this like PPPoE, which is not very widely used these days, but still, it supports most of the features that you might need to build any solution around the Ethernet connectivity. Now let's just talk about the SPI interface, because SPI is the protocol that we will be using to communicate a microcontroller with this W5500 module to put the internet connectivity. As I said, the SPI mode 0 will be used. It also supports the mode 3, SPI mode 3, but I think it's good to go with the SPI mode 0. I think it worked pretty well for me so far. In addition to SPI lines, we need two more additional lines. One is a reset and one is an interrupt. So you have a standard SPI signal like MISO, MOSI, serial clock, then chip select. You need some more apart from this. So for sure, it will take few more IO lines from your microcontroller. The SPI interface, there is very strange type of SPI interface this W5500 module supports, wherein you connect the CS line, chip select line, forever to the ground. And this is called fixed length data mode. I'm not a huge fan of this mode, but it does support this FDM mode. We'll talk about it a bit later. What it does is it allows you to put the W5500 connectivity with less pins, but you have to sacrifice the other features, like you can't connect more SPI devices to the same SPI bus, and that's not really good. But it does support in case if somebody wants to build a solution where they are really tight on the pin counts. Then when you write an SPI interface for this chip, you have to make sure the MSB bit, the most significant bit, means the 7th bit into the byte, will be sent it first. That's how, if you're configuring the SPI interface on the microcontroller firmware, let's say on to the Q by DE or something, then you have to really make sure the setting has to be correct. Now let's just talk about two-way through which this W5500 module will talk to any microcontroller. So the first one you can see on the left side, we have this CS line on W5500 module, and that is connected to ground. So the CS is tied to ground for forever. And this version is called fixed length data mode. Okay, and that you can see here is a microcontroller. Microcontroller could be anything. We'll take STM32 microcontroller, but it can talk to any microcontroller, of course, which supports the SPI interface. Now, if you look at the right side, the second way you can interface, the slave device W5500 module will talk to the microcontroller by connecting the CS line, chip select line, to the IO pin of the microcontroller. This is the normal way. So this is a normal way, which is called variable length data mode, VDM mode. This is what I prefer, because if you use a variable length data mode, then you can connect to the same SPI bus. You can connect a multiple SPI devices. So you can connect SPI flash, you can connect SPI SD card interface or something. But if you use FDM mode, fixed length data mode, then your CS will be tied to ground for forever, and you cannot able to connect anything else to this SPI bus which you have dedicated to W5500 modules, right? I hope this makes sense. So the implementation that we will see today is the variable length data mode, okay, wherein the CS pin chip select will connect to the GPIO pin, or the CS pin, chip select pin of the microcontroller. We'll see into the implementation, but this is the two ways we can connect. Now let's just talk about driver library, because this driver library is provided by Viznet. And one thing that I want to really quickly talk here is this chip has very amazing documentation, and also has very well documented this driver library. And this driver library is called IO library, Internet Offload Library. Now, why this is just, I believe, the reason why probably this is Internet Offload Library is because the TCP IP stack is hardwired onto the W5500 module. That means the TCP IP is implemented inside the microcontroller. So, sorry, inside the W5500 module. So in the microcontroller firmware doesn't have to do that heavy lifting. So all this TCP IP related stuff will be taken care by W5500 module, and that will be taken care by this IO library, which is what the driver library is. And if you look at the structure of this library, you can see this is the W5500. This is a device that we will be using, 5 chip. Remember, the Viznet has several other products like W5100, W5200. These are like other products. So because we are just focusing on W5500 module, these are just the source and header file. These are the device specific source and header files. And then there is a socket, and there is a vizchip config.c. These two are common files for any interface with the Viznet chip. Okay, so these are actually just a 2 device specific file, and these are like a common files when you port this IO library into your microcontroller project. Doesn't matter which microcontroller you use, the process remains same. It does not include, this library does not include microcontroller specific code. That's why I said again and again, you can connect to any microcontroller, even 8-bit microcontroller, which has an SPI support, like 80 mega 328 microcontroller, say for example, on to the Arduino Uno. And by the way, you should know that the Arduino Ethernet Shield 2, the second revised version of the Arduino Ethernet Shield, uses the same chip, W5500. Okay. The library, the source code is compiled by C compiler in any platform because it's written in pure C code. And all we have to do when we port this IO library into our microcontroller project is to write the low-level SPI. Okay, so we have to write the low-level SPI functions to read and write, and that takes care the W5500 functionality to be accessed through the microcontroller firmware. I will show you live, but these are the cool things about this IO library, which makes unique in itself. If you want to download these drivers, these are free. You don't have to pay anything. It's just a free. You can just go to the GitHub page of this Viznet, and then you can download. I will show you the project structure because I have off the shelf downloaded and integrated into my project. Now let's just talk about how the actual physical connection happens with the microcontroller STM32, the W5500 module, and the TCP client that we are using. Okay, so here we have a Nucleo 32 board, which has this STM32 303 microcontroller, and this has an SPI bus support, SPI1. So it has this typical MOSI MISO serial clock chip select pin, and they are connected to the same SPI pins onto this module. These are pretty straightforward. If you look at the back side of the module, every pin has a label, so it's very easy to connect. So over SPI interface, we connect the microcontroller to this W5500 module, and together this PHY chip and the STM32 microcontroller build the TCP server. We will write a firmware which will make this as a TCP server. And then through this RJ45 connector, we will be using a LAN cable, which I showed you into live demo in few minutes, in early few minutes of the session. So we will connect the LAN cable to our host PC, to our laptop, and on our laptop, we are using this TCP client software Hercules. It's very powerful software. You can configure so many features, but we are just limited to TCP client. So we will be configuring it as a TCP client. And you can see there's an IP address, TCP server's IP address, and then the port number. So when the TCP server is running onto the microcontroller, we will put the IP address and the port number. And then as soon as we click the connect button, this client will connect to this TCP server running onto this microcontroller. I hope this makes sense. Now, we will be connecting an external LED to PB0 pin. So what happens is when we write here a text message on, and when we press the send button, this on text message will be sent through this LAN to this TCP server. And as soon as the server received it, turns on the LED. Now, in order to respond back, this web server, this TCP server, not a web server, TCP server will respond the text message that LED is on. Similarly, if you send the message off, you will receive the response back, LED is off. This is implemented into the firmware. But I hope this gives you a very detailed idea how this TCP client can able to talk to this TCP server running onto this STM32 microcontroller, which is possible using this W5500 modules. Okay, and these are the pins that I have connected, like a MISO pin connected to PA6 pin, MOSI is to PA7. This slide will be there for downloads if in case you want to see. This LED is connected to PB0 pin, so you can later look at this pin number and connect accordingly. The source code also will be available onto the GitHub page of DevHitch, so you can download the source code as well to try and test by yourself. But this is how the connection will work out. Now let's just talk about the TCP client that we will be using, and it's Hercules, which is free to download. You can download from the official web page. The good thing about this TCP client is you can use it as a TCP client, you can use it as a TCP server, or even for UDP, you can use it. Even in fact, you can configure the serial client. So there's a serial option here, but it's none of our interest for this session. So I'm just using this TCP client option, and we have to just put the IP address of our TCP server and the port number. And you probably know that every server has the IP address and every server has the port number, right? And that's how the client will connect to the server. So this is the reason why I chose this TCP client. And you can send multiple messages through this multiple windows to send. And I love this feature. Now, since we will be communicating two devices over the Ethernet network, so one device will be our computer on which the TCP client is running, and the other device will be our STM32 microcontroller along with W55 W5500 chip, which is a TCP server. So this two device has to be into the same network, right? Because I will be creating a small network from my computer's Ethernet setting, and then I will bring in all these devices into the same network. And that's why this network configuration is very important. I hope you know that any Ethernet device, when you connect to Ethernet switch or your router or something, it will be detected. Let's talk about a computer. So when you connect any Ethernet device to your computer quickly detect the Ethernet device found. Just like when you connect a USB stick to your computer, it detects the external drive, right? So as soon as, like in this case, when I connect this W5500 module to my laptop, it detects as a Ethernet 2. Can you see this Ethernet 2? So I open up the properties of Ethernet 2 and I go to the IPv4 setting, and there I have to put manually, because this is a static IP address that we are assigning, and I will tell you why I did it. So we have to statically assign the IP address for this device and for this network. So the IP address is defined 192.168.2.2 for this case, and the default gateway will be 192.168.2.1. Now you will say, okay, why have I used this 2.1 in the first place as a default gateway? Let me show you. Let me go to my computer and just open a command prompt, and if I run IP config. You see my laptop has the IP address 192.168.0.1. So I thought maybe it's a good idea that I use the range of this IP address where 2.1 will be unique. So it will not conflict with my internet's IP address, means the access point that I'm using to access internet for this live stream. So that's why, to make it unique, I use this, and the subnet mask is 255.255.255.0 in the end, and this works pretty well because this is not a very big network. In this simple small network that we are creating, there are only two devices. One is my laptop, and the other device is W5500 module with the STM32 micro. Just the two devices, so it doesn't matter. Just put this 0 and this goes well. We will discuss this if in case you have a question into our Discord server. This is very big topic, but I hope you get the point. Like, this is how we create a small network, and in that network we connect our devices, like uh, the STM32 microcontroller. Now let's look at the project structure. Okay, so I created this project called TCP server. I will take you to the real project into CubeIDE, but before that I want to show you something. So I created this project TCP server because we want to host the TCP server onto STM32 microcontroller. And this is the library downloaded from GitHub. And believe me, I did not deleted anything. I just extracted and ported into my CubeIDE project. That's why you can see all other products from the VizNet is shown up, like W5100 module. This is the old Arduino Ethernet shield. Then W5500, this is for the new Arduino Ethernet shield users, right? The one that we are using today for this demonstration. So this W5500 include the device specific source code. Okay, there's two source and header file. And then there's a socket and there is a wizchipconfig.c. So these are the common file. I will explain in very detail. Just hold on. What I want to make my point is porting this IO library from VizNet to any microcontroller is very simple. You just have this 4 and 2, 6 file to be ported into your microcontroller project. The one reason why many people use this W5500 modules into the project is because this integration of TCP IP stack, which is hardwired onto this chip in itself, is very easy to be implemented through just porting the library into the microcontroller project. Okay, the simplicity, there's a saying that says simplicity is ultimate sophistication, right? And that's exactly goes very well with this W5500 module. Okay, I hope this makes sense. Now let's go to a real project and show everything in to the action. So here's the Cube IDE, and you can see this is the project I was talking about, TCP server. And here's the folder that I downloaded from the GitHub, and I just added this folder into my project tree. And as I expand, they have a plenty of applications, example codes for very many different protocols like HTTP, MQTT, or something like that. But all what we care today is the Ethernet. So if I expand Ethernet, you see this W5500 folder, and this two source and header file will be added into the project. And this two files takes care all the API. And by the way, this APIs are the BSD style API. So if somebody have done a socket programming, network programming onto a computer in C or in Java or something, they would feel already comfortable with this APIs when they will be working with the project. That's also a good thing. So these are the device specific files, and the socket.c and the visconfig.c, these four files, including source and header files, these are the common files. Okay. So let me just talk a little bit about this file. So these are these two files gives us the API that we want to access through this W5500 module. But the socket.c file will gives us a function which will allow us to implement the TCP socket. This is very confusing into the network when I started learning these things in the first place. To create a TCP server onto the microcontroller, all what we have to do, especially with this W5500 module, we just have to create a TCP connection. Once we create a TCP connection, some people call it as creating a TCP socket, the connection. Then as soon as we create a connection, we then listen to the request coming from the client. And that all things means creating a socket will be taken care by this socket.c and socket.h file. And then with chipconfig.c file and header file, here we do the configuration. All right, we'll get into that bit later. But this is the structure of the code is. Now let's go to the implementation. So the code starts, before even the code review, let me just take you to the IOC file for you to get the understanding of the connections. So you will have the firmware and the hardware connections, all these things very clear. So it takes few seconds, I guess, to load the IOC file. But once it's open up, you then can able to see that which pin is connected to which SPI lines. Okay. So let's look at this. Let's dissect the connection. I hope it's visible now. You can see the PA4 pin, it's a GPIO that we are using for the chip select, and PA5 pin connected as a serial clock from the SPI, PA6 for the MISO, MOSI, and the LED is connected to PA0 pin, right? And if you want me to get into the clock setting, look, clock configuration, I'm using high-speed internal clock. So nothing, you don't have to change anything. I did not use any external clock or anything. It just configure the SPI lines, and just connect to your W5500 module. Okay, so this is the connection. Okay, now let's go back to the main.c file. So let's walk through the code. So the first thing that we added into the project is the vischipconfig.h. And in this file, we configure which VisNet chip, because as I said, there are multiple products. So we have to specify which chip we want to use from this library. And then socket.h header file to give us access to the socket API. Then if we scroll down, you can see there's a net info. And if you go to this vischipnet, this is a structure where we define the parameter. Like, you probably know that any device that connects to internet has to have a MAC address. So here we are setting up the static IP address. So we just put the MAC address randomly. If you're building a real physical product, then you have to get the registered MAC address. There are many different ways to get the MAC address for your production grade hardware. We'll discuss that bit later because that discussion in itself is a big discussion, but you are welcome to join the DevHeads Discord server and discuss all this tricky things, the production grade. But here, just for demo, I just put the random MAC address into the formats hexadecimal number. Then the IP address, as you remember from my Ethernet IP settings, it's 192.168.2.99. I choose 99. You can put anything. I use 99 because it's too high end that no device will reach, even if there are just two devices into this network. Then the subnet mask remains the same from the setting that I've shown on a computer. Then this is the gateway address, and this will be a DNS. And this DNS 8888 is given because it's a globally accessible from the Google, so it's okay. It works pretty well, so you can use that. And because the way this W5500 connect to internet over this Ethernet, we can connect over a static IP address or the dynamic IP address. So you remember from our previous discussion that we will be putting the hard-coded manually a static IP address. So our IP address will be this one, 192.168.2.99. So this is the IP address we will use on the client side TCP client to access the server running onto this hardware. All right. So this configuration is important in case if you want to try by yourself the dynamic IP address, dynamic host, then you can just uncomment this line which I have commented, and then you comment this line which I have put it. Okay, so I have given the comment here. You can just comment out and uncomment some lines, and then you can play with the static IP and the dynamic IP. It's pretty easy. It's just an API that you have to use. Now, if you look at this WizNet infrastructure, like if I go to declaration, look, it took us to wizchipconfig.h, right? So here we have, again, the comment for you to understand which parameter is what to configure. And yeah, there are a few more things. We'll get into this file bit later, but let's review the firmware. Now, the TCP port, I have given port 5000. Like when you use a protocol, like HTTP protocol is port 80, MQTT protocol is 1883 or something like that. Here in this case, because this will be a local TCP server that's running onto this STM32 microcontroller, I just decided to put this random number 5000, and it works pretty well. You can put almost any number with the same format, and that's okay, because this is not a globally reserved port number, right? So you can put anything. I put 5000, but you should know that it's okay. You can put anything. Now, let's go further into the code. This printf function is basically just to let me use the UART pin to print the debug messages onto the serial terminal. I use a serial terminal quite a lot. You probably have seen in my presentation. Look at this here, along with this Hercules TCP client. I use this, let me press the reset button, and you see the message printed here. So I still feel sometimes like using, and I can move this windows here and there, and that makes me feel good when I work with complex multiple windows and stuff. So I use a UART, and I used it UART. In case if you want to use a serial wire viewer or serial wire debug or something, then we already have made some videos on to the DevHeads YouTube channel. You can check. But this code has nothing to do with the Ethernet or W5500, so don't worry about it. Just let's focus on this few functions that we have to create. And believe me, there are just the 6 functions that I have written. Okay, just the 6 functions. Okay, so the first function that we have wrote is the wizchip select. What it does is it's basically just to take the PA4 pin, GPIOA PA4 pin to low. So whenever you make the CS line low, then the W5500 chip will be selected, right? So this wizchip select function is to select the chip to access the TCP IP stack onto the chip. Then wizchip unselect, because we just have to set the pin to high. Then there will be a wizchip read burst, write burst. Again, you see, we are just accessing read the API HEL SPI receive. So we are using the SPI low-level libraries from the uh, STM CubeMX software or Cube API, HEL API, I guess. But my point here is you can just write low-level SPI functions and then access this W5500. Okay, so this is for this chip read burst, write burst, then read byte, write byte, and with chip in it to start the communication when the microcontroller talks to or try to talk to W5500 module. And the most important thing is this three function. So this registers, reg, with chip CS, CB func, that's a the name itself says CB means a callback function. So these are the callback function for CS, chip select pin. And we passed the function pointer here for with chip select and with chip unselect. So this callback function takes care the connectivity, right? So to whether to when to select the W5500 chip by the microcontroller to establish the network connectivity. Then there is an SPI callback function. So with chip SPI, now here the with chip W5500 using this SPI low-level drivers to communicate with this W5500 chip. And these are again the function that we implemented earlier, few lines of code. And then again, here are a few more callback functions. So SPI, read burst, and write burst. These are the 6 functions that we have implemented. The 6 function I'm talking about: 1, 2, 3, 4, 5, 5, and the 6th one, this one. And this is with chip in it that initialize the chip when it connect to the microcontroller. Means when microcontroller try to talk to this W5500 module. Now comes, because this initialization is very important. If the initialization goes well, then the communication works absolutely fine. So let's look at how this whole thing works. So here we have created this RX TX buffer size. Now remember when I showed earlier slide, I said the beauty of this W5500 PHY chip is it has a 32 kilobytes of built-in memory. Now, I also said like this 32 kilobytes of memory is divided into 16 kilobytes for the receive buffer and 16 kilobytes for transmit buffer. Now, in this chip, this W5500 supports a multiple socket. We are just creating one socket onto this chip. We can, at the same time, you can create multiple socket. And you can create 8 socket. So you see this number 2, 2, 2. So these are 8 times 2, right? And this is for the TX and RX. This is very complex. You have to understand technically mathematics, but this means that out of the 16 kilobytes of memory, like if you multiply 8, because there are 8 sockets. So 8 socket multiplied by 2 kilobytes of memory. So 8 multiplied by 2 turns out to be 16 kilobytes. Get my point? And 16 kilobytes for the RX receive buffer and 16 kilobytes for TX buffer. Together, it's a 32 kilobytes. Oh, it's too much mathematics. Maybe you can rerun the video and try to make a sense out of it. But this is how we assign 2 kilobytes memory to one socket. And the switch chip init function then takes this buffer, RX TX buffer size, and buffer size is same pretty much because there are 8 sockets. And this function basically check link status, check whether the connectivity is established or not. Okay, you know what is link? Link means when the LAN cable physically connect to the RJ45 socket. Then there are 2 things happen. One is the network traffic flow through the LAN cable, and the second thing is your PHY chip. If it supports the auto negotiation feature, then your PHY chip negotiate at what speed the transaction has to happen between 2 devices, right? Ethernet devices that you want to communicate with. And this is basically a function which takes care whether the link is established or not. If it's not established, you have seen like it shows like the device disconnect, right? I showed you in first few seconds what happens when the LAN cable disconnect. If everything goes well, you return value properly and link will be up. That means the connection is established successfully. I will show you the live messages. But then everything else is just the cube IDE generated code. So I don't want to waste your time and my time to explain. So we are calling this chip init function that we implemented in previous few lines. Then we set the net info to put the static IP address to our chip. Then we check if the link status is happened properly. If it happens, it will say link is established, initializing W5500 module. And if everything goes well, then it will go further. And here the actual socket, remember, I explained this. Creating TCP server is basically just, or you can say more professionally when you say hosting TCP server, okay? I feel this little bit funny, but actually in reality as a developer, you are just creating a TCP connection. Once you create a connection, then the socket means the socket connection will establish, and then your device, if it's a server, then it will start receiving the connection from the client. So this function socket, we are using this API socket, and if I right click and let me say open declaration, and you see it took us to the socket.c file. Remember I said this before. The function, the API to create a socket means creating an actual TCP socket is this function. And to create a TCP server, look at this. When we create the function, we say which socket. So we want to create a socket. The first, as I said, there are 8 multiple socket you can create. So the first will be 0. Of course, in the world of electronics and the programming starts with 0. So the first uh, socket 0. Then what kind of server we want to create? Okay, TCP server. Okay, so the connection, which type of connection we want to create, it's a TCP. That's why we put the TCP. Let's say if you want to create a UDP connection, right? So let me just quickly show you. It's not a part of this session, but if you just type SN MR UDP, if you pass this parameter, then the server will be a UDP. And if you pass here TCP, then this will create a TCP connection. Otherwise, it will be a UDP connection if you put the UDP. TCP port 5000, we created this macro, and this will be a flag. So if you pass this 4 parameter, because that tells that we want to use a socket 0, then we have to create a TCP connection on the port 5000, and this will be a flag, and that's how the socket is created. Literally one line of code, right? So this API allow us to create a TCP connection onto our microcontroller. And I will not explain this if else statement. If you know a very basic C programming, then it's just checking if the socket connected properly. If it's written value 0, we'll not get into that. Just remember, as soon as our code execution starts, and the code execution starts into the microcontroller to the main function, and the first thing happens is to create a socket, because we want to create a TCP connection. And in the never ending while loop, as this code execute into the memory of the microcontroller, we check if the link status, because throughout the process, we have to always make sure the link is established, the connection never lost. Okay, because sometimes the network just disappear and the device get disconnected. So you have to check all the time, check link status, and then check if the status remains active in the process. If it's not active, then you send the reconnect request again and all these things. But in the never ending while loop, we create a TCP connection again on the same socket, 0 TCP connection. This is all things. And when we create this socket, once it's the initialization, and then we have to do it forever into the memory of the microcontroller. Then we are checking if the connection is established. Then we have to check here into the code. I can just quickly scroll down. You see we are checking the received message. If the received message is on, then this LED connected to PB0 pin will light up. Okay, on message. So once the socket is open, the TCP socket is open, TCP, then it's listening to the connection coming from the TCP client, and our client is basically our Hercules, right? So let me show you. So when I go to this Hercules client, okay, and because there are a lot of jargon here, let me just clean for you to understand better. Let me just look at, this is our TCP server's IP address, 192.168.2.99, and this is a port number that we define as a macro. And if you don't remember, because if it has gone very, very fast, let me just confirm again into the code. Look at this, 192.168.2.99. This is where we assigned the static IP address to our W5500 module, right? And this 5000 will be the port. So as soon as we put this information, like this is our server's IP address and this is the port number, and when we click on connect, then the TCP connection, this TCP client connection established with the server, which is running on the STM32 microcontroller. The moment I type here message on and I press the send button, the LED lights up because this TCP client sent this on message, the text on. Look at this code here. Let me just quickly go through. Okay, so it set the GPIO, like PB0 pin to high, that turn on the LED, and then look at this TCP TX buffer transmit buffer, and it transmit the LED is on message. In case if we press the second send button, which is the off message, when I press the off button and look at the code, the off message is received, the GPIO reset, that means the LED turn it off, and then this response text message LED is off will be sent it back to the client. That's why on a client we get this LED off printed. Make sense? This is how the communication is happening. And by the way, just let me show you again. This is a serial client, and clear data, and let me just disconnect. You see this is talking in conjunction with this serial terminal. So when I say connect, you see the message shows up here as well. So when I press on, LED on, see the message comes to the hardware, right? So hardware is receiving this message to 2 bytes. And when I send off, look, it says receive 3 bytes. So the server is receiving 3 bytes OFF. Every English character is 1 byte. So there are 3 bytes for the off and 2 bytes for the on message. I hope this clears up everything. Everything else is just error checking into the code, whether each line of code executed properly or not. Let me show you the final demo wherein I built the project. Click the hammer button on the top left corner for you to see. And feel free to download this code from the GitHub page, the DevEd's GitHub page. So there's 0 warning, 0 error, 6 warning, it's okay. Warning, you can turn off the warnings. That's not very important. So the code is uploaded. Let me clear, right click and clear window, disconnect. So let me again clear. Sorry, this is very difficult live demo. That's why I used the static IP address. So now the fresh new piece of firmware is running on a microcontroller. Just for your confirmation, you see on my camera, I have this real physical setup onto the webcam, and let me press the reset button and see what happens onto the both terminal, right? So here onto the serial, it says the WizNet function registers, and this WizNet functions are that 3 APIs callback functions in which we pass the 6 functions that we have wrote into the code. And then it says the link is established, initializing this device W5500, and TCP server is listening on port 5000. Again, I show you the demo for you to remember the auto negotiation feature. If I disconnect the LAN cable, it is difficult on the camera. Okay, I can't do it, so I can remove it from my switch. So now I disconnected. You can see So it stays connected here, but I have disconnected from my physical hub on the computer. So right now it's printing, waiting for link. So as soon as the device gets the internet connectivity, you can see it's re-listen back again, and it says the TCP server is re-listening, right? And let me click the connect button. You see the TCP client is connected. The server is running onto this STM32 microcontroller. And let me just press the send button. You can see everything in sync on a webcam. So the LED turn it on, and then the message comes to client from the server, and on to the server, the LED turn it on. And when I press the send button in front of off message, the off message will go to the TCP server, and then the response comes back again to the client. LED is off. So turn it on, off. This proves the point, right? This is very typical client and server communication. You have seen live in action. So let's come back to the presentation again. And I don't want to waste the time. Let's quickly summarize. We have in the market, we have W5500 module, which is a simple and easy to integrate, as we have seen today. Because this W55 provide the MAC with the 5 and the TCP IP stack hardwired onto the chip. Now, the great thing about this chip is it supports 10 and 100 Mbps speed. The other solution which people often choose, developer in the market these days, is from the microchip technology. It's a product called ENC28J60. This is again interesting because it's the cheapest Ethernet PHY you can buy. It supports 10 Mbps, so it doesn't support 100 Mbps as like W5500. So if you're working with the audio and video file where the size is too much, then maybe this ENC28J60 doesn't make a sense. But for IoT, where you are just sending a sensor data or something, just the messages, textual messages, then I think ENC28J60 to cost optimize your product makes sense. The other problem with this chip is that when you implement an TCP IP stack, you have to implement and use the memory of the microcontroller, because this chip doesn't have the hardwired TCP IP stack right in it. And as I said, it's a chip and it has a MAC plus 5 but doesn't have the TCP IP stack. So TCP IP stack has to be implemented onto the microcontroller. The third option, the third choice many developer uses is to choose a microcontroller which has a built-in Ethernet. And the advantage that you get is the high throughput you can achieve with this microcontrollers, low latency, but you get just a MAC. So you get a MAC, but then for 5 and for TCP/IP, just leave it because it will be done in the software, but the 5 chip has to connect it externally, right? But the question is, when you choose the MCU with built-in Ethernet, it's for multimedia media application where you are dealing with a data with very high throughput and audio video, which is very sizable data, big chunk of data. These days you can find a microcontroller from NXP, ST Micro, a lot of different microcontroller, high-end microcontroller. These are a little bit expensive as compared to normal low-cost microcontrollers, even 32-bit. Let's say Cortex M4 architecture, M4 or M4 plus, whatever the ARM architecture is. You can find this MCU with built-in Ethernet controller. But sometimes what happens is, if you build a solution wherein you are just building very cost sensitive product, it doesn't make a sense to put maybe a chip which in itself will cost $8 or $10. I don't know, it depends. Like, I live in India, so dollar rates really makes the difference when you choose the solutions. But yeah, so you have to make sure it should not overkill your requirement. So sometimes I still see that W5500 does works. ENC also works for low end, low requirement. So this is how you choose, different Ethernet controller and PHY chips in the market. I hope you have learned something out of this session and you found it interesting. Thank you very much for being a part of this session.
Thank you, Umesh. Always great stuff. If you're wondering, If I'm in a different room, I am, because I had to get closer to the router. We have a couple of questions real quick. Let's see if we can do this in the next few minutes. Question here is about related to bandwidth. So since Ethernet's usually used in high bandwidth applications, what are the memory implications if you're streaming, video or audio? Do you need to select an MCU with a larger SRAM? Or maybe use an external FIFO buffer to handle a high-speed stream? That's from Edwin.
Yeah, I think that's why for the high-end requirement, as likely what you said, you use a microcontroller which has a very decent size of memory. And we have to agree, like these days, you can have a microcontroller with 512 kilobytes of memory, or I mean the size of RAM and the flash is increasing. And if you look at the H7 or F4 microcontroller, let's say ST series, right, you have very good amount of memory that you can use to offload this heavy lifting stuff. And you can also use a DMA from the microcontroller to handle this very high throughput data. But if your requirement is as such, obviously you would just choose a microcontroller which has a built-in Ethernet controller. Yeah. You can always have an option to interface external memory and offload your data if you want, right? That's why in the microcontroller these days we get a crazy interfaces like 4 SPI, 4 I2C bus, right? And there are a lot of things. Yeah.
Great. Another question here. They've got a couple of different people who are asking about automotive applications. Let's see which one. I just was cycling between the two of them. Yeah, so I guess one of them is just what's the use case in automotive?
I think in automotive these days, because there's a lot of media applications out there, right? Very high-end displays, right? Very high-end media integration. I'm not automotive guy, but I would just say in general, you need very high-speed communication, which, let's say, when we talk about the old-fashioned Ethernet connection, that's a 10 Mbps. And then we saw today W5500 can give you 100 Mbps, right? Now, there are the Ethernet Mac Ethernet controller that can give you 1,000 Mbps speed, right? 1,000 Mbps. And I think with such a speed, you always, even in automotive, try to get Ethernet. I mean, you can have an automotive Ethernet in itself is a separate category, right? So the modification of Ethernet or the application of Ethernet in automotive. So you can see a lot of applications. I tend to work a lot with Industry 4.0, so not very much in, but you can just quickly search and go through some automotive specific Ethernet files, right?
Great. I think we're running out of time. There was one other question. One of them was again related to data loss because of higher bandwidth things. I'm assuming that that's always the case, and that your last response addressed that with respect to the memory.
I think I need to add one more thing. If you, especially for high-end applications, okay, let's not talk about the cheap cost optimized product. When you use a high-end microcontroller, let's say if you use STM32 F4, what was that? I don't remember top of my head, but or maybe H7 series, right? F7, F4, F7, H7. So when you try to access this LWIP or other stack from the micro, you can get even the OS support into this microcontroller with such a high advanced throughput and speed, right? So, and that too provided by the MCU vendors. So you have an RTOS and your libraries is compatible with it, and you just have to integrate. And I think with this scenarios, like how this vendors are providing this library, let's say if you use STM32H7, you can have an TCP IP stack with a ThreadX RTOS, right? I hope I'm right. The name ThreadX is bought by Microsoft, right? So that is the implementation of the shelf, but it doesn't have implementation for FreeRTOS, right? But ThreadX is very popular and is very stable. So you can do a lot of things, even if your requirement is very high throughput, low latency applications.
Yeah, great. All right, everybody. Well, some other questions related to specific devices and implementations. We probably won't have time to do specific sessions on that, but I recommend setting or joining the Discord and asking questions there, and we'll see if the community can help you out. I want to thank you, Umesh. Always great. And then we have another session coming up in a couple of weeks to continue this series on Ethernet. Do you want to give a quick overview of that, Umesh?
Yeah, so basically, Ethernet, as I said, I'm a guy who worked with industrial IoT applications. And in industrial IoT, Ethernet is very, very alive. And one of the use case very often we see is a Modbus TCP IP, right? So I understand there are a lot of applications that are revolving around OPC, UA, and all things, but still, Modbus TCP IP is still dominating. So the use of Ethernet, the thing that we have seen, W5500 to establish the Ethernet connection, it would be amazing into the next engineering hours to see the application of W5500, where I will be implementing a real Modbus TCP IP stack on it. And I will show you a Modbus TCP client can talk to Modbus server, which is running on STM32 microcontroller. So it would be amazing if somebody wants to see how this Modbus protocol works with the network, then it would be amazing. And I'm looking forward to see you.
That's great. All right. Well, check out the DevHeads Discord server at discord.gg/devheads or go to devheads.io. You can find out more information about that session coming up. And you can also find out more information about Ethernet and IoT and embedded development in general. Ask Umesh and other experts there who can help you with your questions. Thanks a lot, guys. Really appreciate your time. And we'll see you in the server. Thanks, Umesh. Have a great weekend, everybody.
Thank you. Bye-bye.